Building on our earlier discussion, let us explore the perceptron in English to grasp its foundational role in artificial intelligence. Think of the perceptron as the simplest form of a neural network, designed to mimic how a biological neuron processes information. It acts as a binary classifier, taking various inputs and deciding which of two categories they belong to. This elegant model, created by Frank Rosenblatt, serves as the essential starting point for understanding how machines learn from data. To understand how it works, we start with the inputs, which are the raw data points the model receives. Each input is assigned a specific weight, reflecting its relative importance to the final decision. We calculate the weighted sum by multiplying each input by its corresponding weight and adding them all together. This mathematical core allows the perceptron to prioritize certain features over others, much like how our brains focus on specific signals while ignoring noise. After calculating the weighted sum, we add a special component known as the bias. You can think of the bias as an extra weight that is not attached to any specific input. Its role is to shift the decision boundary, giving the model more flexibility to activate or remain silent. Without this bias, the perceptron would be forced to pass through the origin of the coordinate system, which limits its ability to fit complex real-world data accurately. Once we have the total sum including the bias, it is time for the activation function to do its job. In a classic perceptron, we use a simple step function to determine the final output. If the total sum is greater than or equal to 0, the neuron fires and produces an output of 1. If the sum is less than 0, the output remains at 0. This clear binary result is what allows the machine to make a definitive choice. Let us look at the full mathematical logic of this process. We take input 1 times weight 1, plus input 2 times weight 2, plus the bias term. This entire expression is then passed through the activation function to generate the final classification. While this might seem simple, this linear combination of inputs and weights is the fundamental calculation used in even the most advanced deep learning architectures today. It is the basic unit of computational intelligence. The true power of the perceptron lies in its ability to learn from its own mistakes. During the training phase, we compare the predicted output with the actual known label. If the prediction is incorrect, the algorithm calculates the error and slightly adjusts the weights and the bias. By repeating this process many times across a dataset, the perceptron gradually finds the optimal values that minimize errors and improve its accuracy over time. However, it is important to remember the limitation we mentioned earlier regarding linear separability. A single perceptron can only solve problems where a straight line can separate the two classes in a dataset. If the data points are mixed in a way that requires a curved boundary, a single perceptron will fail to find a solution. This realization eventually led researchers to stack multiple perceptrons together, creating the multi-layer networks that power modern technology. In summary, the perceptron is a beautiful example of how simple rules can lead to intelligent behavior. By combining weights, a bias, and an activation function, it creates a linear classifier that can learn from data. Understanding this unit is the first step toward mastering neural networks and deep learning. From these humble beginnings in 1958, we have built the complex systems that now recognize faces, translate languages, and drive autonomous vehicles.